Okay. I hope everybody can listen to me. I'm Abdul Rahim Nizamani. I'm a PhD student in the University of Gothenburg in Sweden, and this work is in collaboration with Jonas, Juel, Persson, and Claes Strannegård, who is here. I'll present a computer program that's in succession of previous programs that we have been presenting in the previous AGI conferences. And this one is called Alice in Wonderland, inspired by the story of Alice, who fell into an exotic world, but she was able to use her capabilities to learn and reason about that world. So AIW is a program, a system that can learn and reason in formal systems. For example, arithmetic, logic, and to some extent, non-ambiguous natural language. It uses some inspiration and some concepts from cognitive modeling, although it cannot be called a cognitive model in itself or a cognitive architecture, but it uses some of those things and some algorithms from AI. It can perform deductive and inductive reasoning in formal systems. It's based on our model about bounded cognitive resources, and I'll talk about later. And it's in continuation of our previous work, which did the same things, but it required fairly well-designed examples to learn from. This one, on the other hand, accepts completely random examples and builds up a theory from that. Perceiving or coding knowledge in the system is done by, first I define what a domain is. You know, there can be many different domains, and this one is supposed to be domain independent. So it can accept any arbitrary domain expressed as a set of facts, and a stream is as a sequence of facts from the domain to the program. It can either be a random stream produced by the program, it can be a file which can be uploaded, or it can be interactive by a human providing the examples. And the facts are negative or positive, composed of terms. Terms is the basic unit. It represents a single or complex concept. It's a binary tree labeled with symbols, which are strings only, or variables. So the program has an intrinsic notion of variables, but it does not have any notion about data types. So the top one example is 213, but 2 and 1 and 3 are strings here, not numbers. Or x plus y, and the program knows that x can take on any value. And the knowledge is represented by rules. Rules are fairly often used in other cognitive architectures as well. Rules are here, the rules rewrite something into any other thing. And here are the basic types of rules that we use. The deep rule preserves equivalence. So if the two things are equal, you can replace one thing with other inside a larger expression. On the other hand, shallow rules are like implication. So they are necessary in some logic systems. They do not preserve equivalence, and they cannot be applied deep in this system, even though in formal logic they can be applied deep under certain conditions. But for simplicity, we just assume that they can rewrite the whole expression into any other expression, but they don't apply inside it. And negative rules are like represent the last made errors by the program. Inspired by functional programming rules, we restrict the rules to be pure, such that they cannot introduce a new variable or a new complex concept inside the right-hand side, for which we will have to search infinitely. In formal logics, this is rather okay. You can introduce anything, But for computability reasons, we assume that the rules should be pure. How does the system reason? It reasons as a term rewriting system. It produces computations, which are a sequence of terms. Each term is computed by applying a rule to a previous term, and we use standard search algorithms to search for the shortest computation for any given expression. The computations can be very complex and big, but inspired by cognitive modeling, we know that mental arithmetic, when we do mental arithmetic, we are severely bounded by working memory. So the computations are bounded by the working memory capacity, which is the width. The long recognition memory, it is the previous recently made errors, so that the program should not repeat the errors immediately. Span of attention, we can compute certain things to a certain length. And long-term memory is the amount of knowledge in the system, and it should be bounded. So we can put an upper limit on how much the system can learn. Because in different formal systems, the complete theory is always a very small theory. We don't need redundant axioms and complex axioms to make it complete. So bounded computations can be generated by applying these restrictions on computations. And here is an example of an unbounded computation. Well, technically it's possible, no problem, but for computability it's quite complex and requires a lot of time, especially when these computations are repeatedly used for learning. We need the computations to be small enough. Here's a bounded computation in logic. It's basically a goal-oriented proof or a computation from the goal to the value truth by applying logical axioms. How does the system acquire new knowledge? Because in the beginning it is a complete empty long-term memory or theory. You can start with a simple theory as well if you want. So it acquires new knowledge by adding a rule to its memory, and it can remove any number of rules if they are found wrong. But it can only learn a single rule. And for that it has to decide, because for any given observation from the stream of facts, there can be more than one small theories that can account for it. So it has to select one theory that is at present the best theory. Learning occurs, the simplest form of learning is just memorization, so it can learn the fact itself. It can form abstractions of facts by replacing constants with variables, but then it requires more evidence than just a single fact. So 0 times 1 is 0, but that doesn't mean that 0 times x is 0. That could mean x times 1 is x, but so it needs more than one examples. And that's an algorithm that computes how much minimum evidence it should consider, or it should have to add an algebraic rule to the memory. And it can be further algebraic rules. There are some other types of rules, which I'll not go through. Synonymous words for language learning. For example, nouns can be replaced with other nouns without making the grammar wrong. And it can learn inductive function definitions. For example, patterns that generate number sequences. So given a small sequence of integers, it can find a small pattern that can extrapolate that number sequence. But it's independent of numbers, so it only considers numbers as terms. For finding the evidence, the system depends on the observation, but it can also try out random values for variables and try to compute two sides of the rules independently And if they both converge at the same value, that means this set of values for variables satisfies this rule. And if they don't converge and it finds a single divergence example, which means two sides compute to two different values for any given value, that means the rule is wrong. So it needs more than one evidences or convergences and no local divergence. And local here means within the theory it has already acquired, not in the domain. It cannot ask from the user or from the domain whether this is true or not. That is another possibility if we consider an intelligent student who can ask a teacher. As I said, for any given observation, more than one theories can account for it. So the program uses a simple criteria for selecting one. And we know that basic knowledge of small facts, such as, for example, tabular facts in arithmetic, they are necessary. Any number of axioms without considering these facts is insufficient to prove compute in arithmetic. So small facts are always preferred. Usefulness, simplicity, by considering Occam's razor, and it's applied in more than one forms. The simplest form is that the length should be minimum. But there are other things as well. Generality, so more variables, more general the rule is. We avoid redundancy in the system because we only want to find the shortest set of axioms that can account for any domain, but that's not necessary. If we allow redundancy, it will acquire many different axioms, for example, all the forms of commutativity and associativity, for example. And that will speed up the computations, but that will slow down the learning. So, but in the end, we hope that it learns a complete theory. I won't go into this because I don't have time. And here's a simple examples how what an ALICE or a fictitious agent sees in the domain from the domain and what it does. In the beginning, it just remembers the facts, and then it slowly tries to form algebraic or mixed rules. Given a stream of knowledge about even and odd or even numbers, whether the number is even or not, it can learn that how to generalize this. So it only needs 10 facts for 10 digits, whether which they are even or not, and a general rule which says that for any multi-digit number, it's sufficient to prove that the last digit is even. And a little more complex is modulo 3, but for that it needs some existing knowledge about addition as well, because to find whether a number is modulo 3 or not, you need to add all the digits together and then find whether it's modulo 3 or not. So given some existing knowledge, it can even form complex things such as modulo 3 operation. It's implemented in Haskell and with graphics so that it can be easy to use and test. And here you can see that in the left-hand side, it's ALICE, a fictitious agent and its memory, with the facts and hypotheses separated for easy checking, and a wonderland or a domain, which can come from the program itself, because I've implemented some domains, a random generation of facts in arithmetic, logic, or language, or it can be a file uploaded. It can learn many domains. I'm not sure if it can learn all possible or all existing logic, symbolic logics, but it can learn fairly good things. Arithmetic, propositional logic, quantifier-free predicate logic, and it can check grammars or learn grammars for non-ambiguous languages. It can also do some analogy problems, like classical Aristotle problems. We've tested it on that. And a previous version of this program, which had a little more, which were more specific, not this much general about any terms, that was able to learn Haskell expressions that are similar to magic Haskeller, although magic Haskeller can form much more complex expressions, but this program could do a little bit of that. So we believe using this Occam's razor and some other ideas from AGI community, we are able to form a system without any stochastic processes, which can learn formal systems and domains, any arbitrary domains. And we use this deductive component to enable induction. So for any set of theories, we try to compute them using this term rewriting system. And with these bounded computations, we make sure that only those theories are considered which are easily computable, which is another notion of simplicity. It's not just the length of a pattern, but its computability, which should also be accounted for. And thanks for your attention.